Hello, I'm Craig Parker from WIT's Planetary Health Research. Today I'm presenting a journal club discussion on a fascinating 2025 systematic review by Rahmani and Sharifi titled Urban Heat Dynamics in Local Climate Zones. This paper analyzes how different urban morphologies drive heat accumulation and examines evidence-based mitigation strategies for creating climate-resilient cities. Hello everyone and welcome to today's journal club. I'm presenting a fascinating systematic review published in 2025 by Rahmani and Sharifi titled Urban Heat Dynamics in Local Climate Zones. This paper provides a diagnostic review of how different urban morphologies drive heat accumulation and what mitigation strategies actually work. As our cities continue to grow and climate change intensifies, understanding the thermal anatomy of urban environments has never been more critical for public health. Let's start with the problem. The authors frame urban heat using a medical metaphor that's quite instructive. First, we have the symptom. Rapid urbanization amplifies the urban heat island effect, directly increasing morbidity and mortality risks. Second, the diagnostic tool, the local climate zone framework, which provides a standardized 17-class system to categorize urban thermal environments. Third, the diagnosis itself, LCZ2, or compact midrise zones, consistently act as the city's furnace, while LCZ1 high-rise zones present a paradox, and LCZ9 is the coolest built zone. Finally, the prescription, morphology-specific mitigation strategies, including ventilation for dense zones, cool roofs for industry, and green infrastructure as a universal solution. The urgency becomes clear when we look at the projections. By 2050, we're facing a surge in global urban population that will intensify lawn use changes. This slide beautifully illustrates the mechanism. Urbanization drives the decline of green space and proliferation of impervious surfaces, which in turn raises surface and air temperatures. The consequence is rising heat-related cardiovascular and respiratory illnesses. The key insight here is that we must understand the city's spatial anatomy, not just treat it as a thermal monolith. Different neighborhoods experience fundamentally different heat dynamics based on their built form and surface properties. This brings us to the local climate zone framework, developed by Stewart and O'Kay in 2012. It's a game changer for urban climatology because it provides a universal language for comparing thermal performance across different cities and climates. The system classifies environments based on three key attributes: building height, packing density, and surface cover. On the left, we see built types, LCZ 1 through 10, ranging from compact high-rise to heavy industry. On the right are land cover types, LCZ A through G, from dense trees to water bodies. This standardization allows researchers worldwide to communicate findings in a comparable framework, which is essential for developing evidence-based urban planning policies. The authors conducted a rigorous systematic review, starting with 812 studies from multiple databases. After screening and filtering, they included 154 studies in their analysis. One of the most revealing findings concerns the measurement divide. The vast majority of studies, 68.8%, use surface urban heat island measurements from satellites, essentially measuring the skin temperature of the city. Only 33.1% measured canopy urban heat island, the air temperature that humans actually breathe. Critically, only 7.1% of studies combine both methods. This measurement gap is important because surface and air temperatures can tell quite different stories about human thermal comfort and health risks. Now let's look at the key results. The authors identified three primary offenders for extreme heat. First is LCZ2, compact mid-rise zones. These are consistently the hottest in both surface and air temperature measurements. The culprit is high building density that blocks wind, combined with lack of height, which prevents adequate shading. Second is LCZ10, heavy industry zones, with high anthropogenic heat emissions from industrial processes and vast concrete expanses. Third is LCZ8, large low-rise zones, characterized by extensive asphalt surfaces like parking lots with zero vegetation. These are essentially heat traps that absorb solar radiation all day and release it slowly at night, preventing nocturnal cooling. Perhaps the most counterintuitive finding is what the authors call the high-rise paradox. During daytime, tall buildings provide protective shading, blocking solar radiation and lowering surface temperatures at street level. However, at nighttime, these same buildings create what's known as the canyon effect. Deep street canyons reduce the sky view factor, meaning heat absorbed during the day becomes trapped, preventing nocturnal cooling. The geometry that protects during the day becomes a thermal prison at night. This finding has profound implications for urban planning, suggesting that high-rise development isn't inherently good or bad for heat, but requires careful consideration of street width, building spacing, and orientation. In contrast, 3 local climate zones emerge as thermal refugees. LCZA, dense trees, is nature's air conditioning, providing the highest magnitude of cooling through evapotranspiration and shading. LCZG, water bodies, act as significant thermal buffers due to water's high specific heat capacity. And LCZ9, sparsely built zones, consistently rank as the coolest inhabited zone because low building density and ample spacing allow for airflow and heat dissipation. The small chart shows the frequency distribution, confirming that LCZA, G, and 9 consistently appear as the coolest zones across temperature measurements globally. This evidence base provides a strong argument for preserving and integrating these zone types into urban planning strategies. The authors synthesized the thermal drivers into 3 categories. First, morphology, or the shape of the city. Inefficient layouts block ventilation, while deep urban canyons trap radiation. Second, surfaces, essentially the skin of the city. Low albedo materials like dark asphalt absorb solar energy, while impervious surfaces prevent evaporative cooling. Third, ecology, the lungs of the city. Low vegetation fraction reduces shade and transpiration. 2 critical cooling mechanisms. This triad of morphology, surfaces, and ecology provides a diagnostic framework for understanding why certain zones overheat. Importantly, it also suggests 3 distinct intervention pathways for mitigation. This leads directly to the paper's mitigation framework, which emphasizes zone-specific interventions. For compact zones, LCZ 1 through 3, the driver is high density and low airflow, so the solution is morphological intervention. Regulate densification and optimize openness to create ventilation corridors. For industrial and low-rise zones, LCZ 8 and 10, the problem is high imperviousness and low albedo, so the solution is material intervention. Deploy cool roofs and permeable pavements to increase reflectivity and allow evaporation. And critically, there's a universal intervention that benefits all zones. Increase green infrastructure. Trees, green roofs, and vegetated corridors provide cooling benefits across all urban morphologies through shading, evapotranspiration, and improving the microclimate. The beauty of the LCZ framework is that it allows for context-specific solutions. The authors present 2 contrasting case studies. In compact high-rise cities like Tokyo or Shanghai, the challenge is blocked airflow. The solution involves creating ventilation corridors, wind paths through the dense fabric, and vertical greening on building facades. In contrast, arid or desert cities like Phoenix or Las Vegas face the challenge of barren paved heat from LCZE surfaces. Here, the solution emphasizes shade structures and water features, though importantly, irrigation-heavy grass is less effective in water-scarce environments. This regional specificity is crucial. There's no one-size-fits-all solution. Urban heat mitigation must be tailored to the local climate zone composition and regional climate context. Now we come to a critical limitation identified by the authors, the data gap in the global south, particularly in Africa. The research bias is stark. The majority of urban heat island research focuses on the global north, with the city type chart showing dominance of large city studies over other classifications. Meanwhile, Africa's rapidly urbanizing or informal settlements present a classification challenge. These areas feature high density combined with unique materials like scrap metal and tin roofs, plus irregular layouts that don't fit standard LCZ 1 through 10 definitions. The result is underestimated risks for vulnerable populations. The authors argue that extending the LCZ framework to better capture these informal settlement morphologies is essential for climate justice and effective heat mitigation in the regions that need it most. So what are the implications for planetary health? The paper makes 3 key recommendations. First, precision planning. We need to move from general citywide warnings to targeted interventions based on LCZ mapping. Second, direct action. During heat waves, cooling centers and emergency services should be specifically deployed to LCZ2 compact midrise and LCZ10 heavy industry zones, where vulnerable populations face the highest exposure. Third, integration. We must combine LCZ thermal data with demographic data for comprehensive heat health risk assessments. This integration would identify not just where it's hottest, but where the hottest zones intersect with elderly populations, low-income communities, and other vulnerable groups. This is the path toward thermal equity in our cities. The authors outline 3 critical research priorities for the future. First, hybrid data collection, combining satellite surface temperature measurements with ground-level canopy air temperature measurements for human-centric accuracy. This would bridge the measurement divide we discussed earlier. Second, refined classification, developing LCZ subclasses specifically for informal settlements and adaptations for the Global South. This would make the framework truly universal. And third, longitudinal tracking, monitoring the long-term effectiveness of mitigation strategies. We need to move beyond before and after snapshots to understand how interventions perform over years and decades, accounting for climate change, urban growth, and maintenance realities. This evidence base will be essential for justifying continued investment in urban heat mitigation. Let me conclude with the paper's central argument, which I think is beautifully captured in this final slide. The LCZ framework provides the grammar to read the urban heat landscape. It gives us a common language for diagnosis. The reality on the ground is that compact midrise, LCZ2, functions as the furnace, while sparsely built, LCZ9, serves as the refuge. But here's the mandate. We cannot manage what we do not measure. Precision thermal zoning, using the LCZ framework to map and monitor urban heat at the neighborhood scale, is the first essential step toward climate-resilient cities. The paper demonstrates that evidence-based, morphology-specific interventions are possible, but only if we first properly diagnose the thermal anatomy of our cities. Rahmani and Sharifi's review provides both the conceptual framework and the empirical foundation for this critical work. Thank you, and I'm happy to take questions. Thank you for your attention. This presentation was created in the interest of transparent education using artificial intelligence tools. The slide design was generated with Notebook LM, narration with 11 Labs, text-to-speech, and assembly with Claude Code. I hope this review of urban heat dynamics has provided valuable insights into the thermal anatomy of cities and the importance of precision thermal zoning for public health. Questions and discussion are welcome.